topic of our today's talk is machine learning. You must have heard this term a lot recently, actually. Machine learning in various contexts. So we'll be basically talking about it today. I'll just briefly go through what we'll be covering. So we'll be actually first looking at why it has become popular nowadays, because it's a old subject like existing from 1950s, but why now that it has become very popular? What are some of the facts about machine learning? Then we will go through a basic introduction. We'll compare it with other areas like stats and data mining, how it's connected and how it's different from them. We will cover briefly touch some of the analytics in machine learning, how it's connected to big data. Then we will go through a formal definition. We will briefly touch some of the techniques in machine learning and some commonly used algorithm and their applications. So to be clear at the start that the objective is not to go to take you through the technical details of the machine learning and all, because those need a lot of time. We basically touching on why it has become important as a subject and what are the common applications. So these are some of the big facts about machine learning. Harvard Business Review 2012, in their one of more very popular article, the topic of that article was data scientist, the sexiest job of 21st century. And data scientists are the one who apply machine learning, that's the title for them. Tech giants like Twitter, Facebook, Google, IBM, LinkedIn, Yahoo, they invest millions of dollars on machine learning. For some of them, most of them, this is bread and butter. Like any feature you see, Google search or LinkedIn, Facebook, they employ machine learning in almost all of their functionalities. It's one of the most popular courses at Stanford for 2013. I'm sure it's still now also. From the career perspective, if you look, US alone faces a shortage of like 140k to 190k people in analytics and machine learning. This is according to McKinsey, and I guess the global shortage should be at least twice of this. So you can see why this has evolved into a very major area in technology. And so let's look at why it has become popular suddenly, because it existed since 1950s. What happened just like last 5-10 years that it has become so important? So first reason is that we have abundance of data now. So just give you some facts that how the data that we generate and we store, that has grown exponentially. Eric Schmidt, who was the CEO of Google in 2010, he said that we generate the same amount of data in 2 days that we have generated till 2003, since the start of time. So since the start of time, what we generated in 2010, we were generating that in just 2 days. And remind you that it's 2015 and probably we will be generating the same amount in a matter of hours now. Another Google paper mentions that by 2020, in just 5 years, the data we store that will go up by 10 times what we have now. And why it has grown so much? The reason is that first thing, the storage costs have come down. Previously you used like tapes and those medium that capacity was not that much and they were costly. So the cost has come down. Another thing is that now we have user generated data. Previously what companies stored was like they used to store the sales data or the people data, but now it's user generated content, social media, and the other thing is complexity of data has gone up. So previously there was just structured data, now we have unstructured data like in the form of pictures, videos, Twitter, Facebook comments, reviews. So all those data it has grown manifold and it is growing exponentially. And due to the complexity, increase in complexity, it's not easy for human to make sense of the data. Previously what happened, the data was structured, you look at sales data, you plot it, you can look, okay, my sales dropped last year, you can probably find out the reason why it happened. But now it's the medium which with company like communicate with their customer data chain that has become social media. So making sense of all that, that is not possible for any human now due to the size and complexity. So there is what machine learning comes in. Another reason is our computation power has gone up. We now have more faster computers, distributed systems, so we don't need supercomputers. We can just make a cloud network out of small computers and achieve the same computation power. And other thing is like the field has matured, both in terms of we have now more tools and methods. Like we now have so many programming languages, tools for machine learning like R libraries, Python libraries, and we have tools like Azure ML. So it has become easy to apply those things. So this is just a layman definition of machine learning, what it is. So machine learning develops algorithm for making prediction from data. So the output of a machine learning is an algorithm which makes prediction from data, and the data is usually past data. Like we as humans, we learn from experience and we like predict our future. Like this happened in the past, so hopefully in the same situation, the same thing will happen in the future. That's the basic premise. So there is a word prediction comes here. So that is a very important word actually. So if you can predict, you can see the future, right? So it's like machine learning in a sense is like voodoo glass. So you can see the future. No, I'm just joking. Don't take it literally. It's actually not voodoo glass. When you say prediction, you should take it in a statistical sense actually. So by statistical sense, what I mean is like something happened in the past, like there were some in particular circumstances, some outcome was there in the past, and based on that we predict the outcome in the future. But one thing is that not the same situation it's not the same outcome every time. And secondly, things that were true in past may not be true in future. So there is always a probability associated with the outcome. So no machine learning algorithm is 100% precise or 100% accurate. There is always a probability of failure and a probability of success attached to it. So it should be taken in that sense. So machine learning is all about generalization. So what do we mean by generalizations? Like what we do is we have data and we try to generalize it to keep it in a very compact and compressed form. Say I have a 1 terabyte of data lying somewhere, or say it was my customer data, sales data. So how do I make sense of it for my future? Like how do I increase my sales or like customer satisfaction? How do I make sense of it? I can't go through that 1 TB of data due to its sheer size or complexity. So I need its essence or it in a compressed form. And that compressed form is given by machine learning, where we develop a model out of it, that's the learning out of it, and then we apply it to make predictions for the future. So an example is like, say you have customer data, you divide them into groups. Say my customer consists of 26 square group, that what I find out from my data, and that's my learning, and now I know how to basically group my customers. And if I see a new customer, future customer coming, I put it into some category. That this is this kind of customer.
Machine learning glitch. This thing that couldn't think much from this coming.
Sorry for the. So what machine learning? I told you what is machine learning, but what's the limitation of what machine learning is not actually. So it's not an exact science, as I said before also. No algorithm has a 100% accuracy or 100% precision to predict the future in a like exact way. So if I tell this to a classical computer scientist, say of 1970s or 80s, they will just reject this algorithm or the whole theory. They will say if something doesn't, if an algorithm doesn't work exact, then what's the use of it? If it can't give exact results to me, it's of no use to me. But machine learning is like that, but it's not an exact science. So, but does it mean that it's not at all useful? Like because it's not exact, so is it not at all useful? So to give you just a short example, say machine learning is widely used in stock trading. A lot of hedge funds use it. What they do is they use the past data and then they try to predict a particular stock price will go up or down in next 1 hour or how much up or down it will go. Based on that, they make trading decisions like buy the stock or sell the stock or go for some other stock. So say they apply some ML algorithm which has some 2/3 probability of success and 1/3 probability of failure. So 2/3 time that the algorithm will make profit for them, 1/3 time it will fail and it will make losses. So overall, if you see, it can still make profit, right? If you can cover their salaries and transaction costs and all, it can still overall make profit for them. Although it's not perfect, but it makes profit. So they will only employ the algorithm only if overall it's making profit. So that's the decision we take while we make our algorithm that sophisticated and we give that much data and experience to it that it works fine for us and may actually serve the purpose. Another example is like you do Google search. So when you type keyword and do a search, usually it's not that the result you wanted appears on the top of the page. The Google uses for the page ranking or machine learning inside. So the result you wanted might be somewhere down the page, or you might have to change your search altogether. But it's still useful. It's not exact, but still useful. So you widely hear the terms statistics, data mining, machine learning, artificial intelligence, all these terms, and they become confusing. Like what is what? Are they related? Are they same? Or are they completely different? What is it? So I would say machine learning sits somewhere between statistics and data mining. I'll just tell you what each discipline does. Actually, stats is a discipline which is more concentrated on the methods or the models. We focus more on methods on the models to solve problem. Like an example is you do correlation analysis in stats. That's a method, but it's not connected to the task actually. We use it for different tasks. That's your call that we will use correlation analysis for it, but it's not attached to a task. It provides a tools or method. Another thing, example is hypothesis testing. Can be used widely for different tasks, but it's not connected to one task. It's one method or tool that given by statistics. And on the other hand, data mining concentrates on tasks. So an example can be, I have 100 different databases from different sources, and I want to identify my customer and their behavior from all of them. So I have to go through like checking common things between them, connecting them somehow, fill some gaps, missing data, replace the missing data, bring data from some other source, do some like derive some data. So here the task is important, what we want to achieve, not the methods. There can be different methods to do the same thing, but here what we are doing is we are focusing on task, and machine learning comes somewhere in between. So it actually connects methods to tasks. For a particular task, we have particular method, way of doing things. So we have trial and testing methods to do particular tasks. You also hear a lot of terms related to analytics, like descriptive analytics, diagnostic analytics, predictive analytics, and then prescriptive analytics. So I'll just briefly go through what does it mean. So you hear also a term business intelligence, BI. So what BI is traditional analytics actually, how they used to do before, and descriptive analytics and diagnostic analytics come under it. What is descriptive analytics? It's like looking at the past data, we see what happened. It gives an answer to what. So like I look at sales data, I see my sales have gone up, but still the profit went down. So I just plot it by monthly and try to look at it. So that is kind of what we plot our data, we produce reports out of it. That's what traditional analytics used to do. Provide reports to higher management, that is descriptive analysis. And we look at past data, that's it, what we past you see there, that comes in the, we just look at the past data and we keep it till there. We just, what happened, just we got that out of it. Diagnostic analytics focuses on why something happened, the why part. So we also look at why, say, the sales went up but the profit went down. So we probably try to find out root cause analysis we do. Like maybe cost have increased, or we build our theory around it, that what might have happened and why it have happened. So that is kind of diagnostic analytics. It also comes under the traditional BI. Next comes the predictive analytics, which goes into the future. So it's a part of machine learning. We learn from experiences and we create a model, try to predict the future, our predictions. So that is predictive analytics. And it answers what will happen, or what can happen actually. One step ahead is prescriptive analytics. So it also attaches an action with the predictive analytics. So it answers how can I make it happen. Like my prediction is that my sales, given the situations today of the market, my sales might go up by 20%. But how do I make it happen? So we attach an action that we have to do these things. These are the reasons why my sale might go up, and so I do these things to make it happen. So these two parts comes under machine learning. So you see the word deployed ML there. That means that what it means that ML works itself to make the prediction and also decide the actions on it. Good example, technical example can be Google AdWords. It looks at your browsing history, see what you are browsing, see what's your interest are, what ad can show. Based on I found out a category that I can show probably a shoe ad to this guy, and then it takes a call or action on that I'll show this Amazon shoe ad on this page. So that's a kind of, it's deployed ML, it runs itself. Humans don't have to see the prediction and take action. So now I'll hand it over to Satya, who will basically start with what's the connection between ML and big data.
Hi folks, am I audible? Loud and clear? Let's get started then. So far you have learned that machine learning is for making predictions on data. Then what is big data for? Let's find the answer. Before I give you the answers, I have got a small refresher for you guys for the benefit of those who doesn't have complete understanding on big data. Couple of weeks ago I was having a discussion with my friend and realized that he was thinking that big data is a framework or rather a software. So I thought next time I'm going to talk about anything related to big data, I'll clarify it for now and forever. What is big data? Big data is not a software, it's not a framework, it's not a tool, it's just data. Enormous amount of data. And what do I mean by enormous? According to the current industry standards now, enormous is anything from 100 terabytes to petabytes. That's big data. And then Hadoop and its ecosystem of projects, they are big data related technologies which will enable you to handle big data, make some computations on it, store in distributed fashion, right? Fine, let's proceed. Now, if you think making predictions on data is a process, then it has got 3 steps to it, right? The first step being collecting data and storing it. Now, and the second step is analyzing and making computations on it. And these are the capabilities of big data technologies. Again, not capabilities of big data, it is capabilities of big data technologies, right? And the third step in making predictions is actually making the prediction, right? And this is the capabilities of machine learning here. Simply put, big data technologies will enable you to handle big data and make transformations on it, store them in distributed fashion, and make computations on it. And when it comes to machine learning, it is used for making predictions from the data. So when the need for the hour is making predictions on huge data sets, then we can use both of them in conjunction. It's not mandatory that both should be used in conjunction, but it can be used, right? Like Anshuman was saying before, the rising popularity for machine learning is because it has become so easy to perform computations and transformations of data now because of the big data technologies, right? There's a saying that more data beats clever algorithms, which means that, see, the fundamental basis for algorithms to perform accurately is having a lot of data, which is basically the experiences, right? So that is why it is famous now. So both can be used in conjunction. To simply put, and to give you an analogy from the life, machine learning to big data is what human learning is to life experience. Here, when we are talking about life experience, it's kind of data, right? Our brain is storing all the experiences in terms of data. That is big data. And machine learning is learning from, machine learning algorithms learns from the big data. The way human brain learns from our experiences, right? Let's proceed. So, now that the context is given by Anshuman and me, let's look at the formal definition of machine learning. Like Anshuman was saying, this machine learning is no new. It has been around for 6 decades, I will say. For the first time, in 1959, this was defined by Mr. Arthur Samuel. He is an American pioneer in gaming, computer gaming, as well as in artificial intelligence. He has defined machine learning as follows. He said that it is a field of study that gives computers the ability to learn without explicitly programming. Right? You can relate that, right? And then now let's look at more formal definition. In 1980s, there is a person by name Tom Mitchell. He has written a book on machine learning. He has defined machine learning the following way. It's more textbook kind of definition. So he says that I have put up the definition in 4 lines so that it will be easy for you guys to understand the components in the definition, right? Study of algorithms that improve their performance P at some task which they are performing, which is T, with every experience P, right? When we say performance P here, for algorithms it is the accuracy at which they can predict something, right? And the task could be making prediction actually. And experience is the data it processes. And then I have put up one layman definition also, which has been picked up from Wikipedia for you guys to put more clarity in the picture. Machine learning explores the construction and study of algorithms that can learn from and make predictions on data. Right? Proceed now. So let's look at what types of algorithms exist. There are more than one way to classify algorithms, but let's look at the classification based on the learning style, which means how we are teaching the algorithm, how we are basically training the model, algorithm model. So, primarily it's classified into 2 types. The first one is supervised learning, the second one is unsupervised learning. In both the patterns, we give input as data, that's obvious, right? But when we come to supervised learning algorithms, we give data with labeled instances in it. What do I mean by labeled instances? We give facts. For example, if we are trying to predict something, if we are trying to predict the price of a house, then we will give what is the size of the house as well as what is the price, cost actually has been sold for. That's a fact we are providing the algorithm. So based on a couple of facts, we are training the algorithm and making it perform better on new instances which it has not seen yet, right? When we come to unsupervised learning algorithms, we still give data, but we don't give any labeled instances to it. So the algorithm has to find labeled instances, the Y part of it, I'll explain that anyway. And then it has to make predictions, it has to find the hidden patterns in the data. Okay. To make it a little more clear, I have put up a little math. I'm sure you guys can deal with it a little bit. X, you can see Y. Y is the variable which has to be predicted, right? And X is the input variables or features, as we say. For example, if you are predicting house price, house size, or the number of bedrooms it has got, these are the features based on which we will make predictions to know how much it can sell for, right? So Y is the variable which has to be predicted, and X is the input variables, features basically, the labeled instances, right? So in terms of supervised learning, we provide X and Y both, which means we are giving the facts basically. We are giving a couple of Y's and a couple of X associated with it, and then asking them to come up with Y for unseen X in terms of supervised learning. In terms of unsupervised learning, we are not going to give them y. It's all x. Complete data set has got x, and it has to try finding y, which is the hidden patterns, and classify them, clusterize them basically. Got it? Let's look at some of the subtypes in this. Further, this supervised learning algorithm and unsupervised are classified into, there are other various things also, but then these are the primarily used ones. This section is primarily focusing on regression, classification, and clustering. Regression and classification, like you are seeing, supervised learning, they are kind of siblings, but they have got their differences. We'll see that in detail in a couple of slides. For now, although the primary types are supervised and unsupervised, I have put up 2 more, which I would say are little hybrid types, which has evolved for past 2 years, right? Semi-supervised learning. It's kind of mix of supervised and unsupervised. In this, what we do is we give data instances wherein we have very small amount of labeled data and huge amount of unlabeled data. So it's a mix of supervised and unsupervised learning. And the reinforcement learning. This is a very fascinating subject which is being evolving because Google is employing this in self-driving cars, reinforcement learning. So what it does is it basically builds a model and deploy it in a dynamic environment without giving any training. It has to learn based on the stimulus, and basically you don't provide any training, and the model learns. If it makes some mistakes, it will be punished. If it takes right actions, then it will be rewarded. Based on that, this model will learn and evolve. Okay, now scope of this session is limited to supervised and unsupervised. I will talk about the regression, classification, and clustering in the coming slides. Let's progress. Okay. Let us suppose we have got a data set like I was showing on the right side. Anybody who has worked on files or database tables can relate to this. This is like rows. We can consider this as a record from the database or a file. So, house size in square feet. That is the X features, as we say. And prices in lakhs. That is Y in the previous slide I was telling. So basically, we have got some facts on how much each size of house has sold for. So this is sample data from a huge data set I possess, right? If we have to make predictions, this data set alone will not help us. We have to plot that. We will use a little bit of algebra. You can deal with it. I just showed you. So take x and y axis, the size of square feet on the x axis and prices in lakhs, and plot this data set on this graph and get rid of the data set, right? So these are the facts we have got. Now let us suppose you have got a friend of yours who wants to sell his house, which is of 1250 square feet, and he wants to know how much he can sell it for. What do? We just try to fit a straight line to the data set which we have got using simple algebra. You know, straight line y equal to x plus c. How we arrive at that is actually the doing part of it. We are not going to talk that now. Okay. So, okay, fine. I have come up with a straight line which I think is an optimal fit, and I extrapolate it, right? And then I will say, okay, probably you can sell it for 60 lakhs, right? But then again, I think about it. Okay, the straight line is not fitting that well into the data set. I get rid of this. I'll go for second degree polynomial. It's a quadratic function, and I will try to get a complex curve fitting, a little complex than a simple straight line. Okay, this seems to be better than the before one, right? And then I try extrapolating again. I'll get 68. This looks more realistic for me. Okay, fine. So I've got a question for you guys. So when we went to quadratic or second order polynomial, the data set is fitting in a better way. So do you think that if you go for third order polynomial, it will do better? Fourth order, it will fit even better and give accurate results? No. There is a problem called overfitting. If you fit too accurately in the data set, right? The generalization, Anshuman is saying that machine learning is all about generalization, which means looking at past data and generalizing it for future data. So for now, you just need to remember that overfitting is a problem, and if you go for higher degree polynomial without thinking about it, it will be a problem. You won't get good results, right? There is a concept about overfitting and how we can avoid that, how to come up with which order polynomial you should choose for optimal fit, but that's out of scope again. It's a complex topic. So, and then since we have given all the labeled data, this is called supervised learning algorithm, like I was saying in the previous slide. Now, in the previous slide, I was saying that regression and classification falls under supervised learning, but then they have got the differences. Now I will tell you what is the difference. The difference lies in the outcome they are giving. In here, in regression, what you see as outcome is a continuous value. And what do I mean by continuous value? It means it can take any value. For now, we are showing 68 lakhs as a figure. It could be 68.1 lakhs or 15 lakhs, 68.2 lakhs, 25 lakhs. It's a continuous. If you take an example, probably the temperature. You can measure temperature to minute details. You can measure time for doing some task. That is a continuous value. We can actually measure it to fractions of microseconds, right? Whereas in classification, the outcome will be discrete values, which means it's a finite set basically. It's not infinite set like in continuous values, right? So for an example, I'll get to that in the next slide. So the 68 here is a continuous value. That's how regression can be differentiated from classification, right? Let's get to the next category. Once again, guys, sorry for the inconvenience. We have to restart the presentation once again. It's not showing the way it is supposed to be. Okay, let's look at classification now. Again, I have got a similar data set, not the same. We have got X as tumor size. We want to make predictions on whether a tumor is actually dangerous for health or not, right? So we have taken a sample data from a data set you possess. In here, we are saying tumor size. I've just put some arbitrary numbers, 10, 15 doesn't make sense. Don't worry about the units, right? And malignant meaning it is dangerous to health. Benign meaning it's not dangerous to health in terms of medical, right? So we have got a couple of facts about the data, label instances, saying okay, tumor size is 10, 15, 20, it's not dangerous for health. And if it is 25, 30, it's dangerous, etc. This has been actually properly diagnosed, and these are the facts we have got. Again, once again, we'll just plot this data in order to make predictions, right? Now we are trying to look at the data and say, okay, plot my data from the data set and get rid of the data set. Now, if we have got a data set here plotted on the graph. If it is Y, let's consider it is as a dangerous to health, which is malignant. And if it is 0, it is not dangerous. Okay, making sense? Now, tomorrow you have a patient who is having a tumor of size that, which is shown there arrow mark. So you can kind of make prediction that it is safe. It's not dangerous, right? Based on the facts you have got. Now look at it. We have got only one feature, tumor size. Based on that, we are trying to make predictions. But probably if we include one more feature, it might get a little more accurate, right? Let us suppose if we consider how early or how late in their life they have got this tumor, age basically, right? We'll see how that goes. And before that, I was saying classification produces discrete output, right? In here we have finite output. Either it can be 0 or 1 binary, because we have got only two classes here. One is malignant and one is benign. So this is a discrete value output. This is not continuous like it was in regression. That's the main difference, right? Let's take age and tumor now. Let's plot. I have got some instances where it says it is not dangerous. It's not dangerous. It's benign. Those are the green ones, right? In the plot. So, and then I have got some more instances which are dangerous for health, and I have plotted them as well. Now the problem is you have got a patient and you have to, and the data instance for tumor versus age is somewhere lying there for the new patient, right? You have to make prediction. What do? You develop an algorithm which will basically separate both the instances optimally. You need not guarantee that, you will not be able to guarantee that everything will be separated properly. It will find the optimal fit to separate the instances. And then what happened? That magenta has turned green now because it's lying on this side of the pane. That's how you do it. Now we have considered two features. In real world, it could be more than that basically. If you have to really make predictions on cancer, then you must look at the thickness of the clump. You have to probably look at how soon, what is the rate of multiplication of cells and things like that, the uniformity of size, shape, etc. So those are some other features in real world scenario. In here, it is very difficult for you guys to see if it is more than 2 dimensions because 2 is right. So I have put up 2 features here, but then in reality it could be more features. And machine learning can scale up to hundreds of features together and give awesome results. Right? And since we have again given the facts for this, it is a supervised learning algorithm. Right? In here also, remember, we have changed. Now we have 2 features. We have increased the features, but the number of classes we are classifying, malignant and benign, they are still same. So 1 is malignant and 0 is benign basically. And then this is the discrete value output. The more number of classes, for example, if you have a digit classification, handwritten digit classification, then you will have 10 classes there, 0 to 9. That is the number of classes will be, right? Let's proceed. Got a small slide just so that you guys are in sync or not. Just go through this. I'll just read it out for you guys. Problem 1. You have a large inventory of identical items and you want to predict how many of these items will sell over the next 3 months. Right? That's one problem you have got in your company. The second problem is you would like to examine a software for individual customer accounts and each treat account decide if it has. Basically, you'll have to find whether a customer's account is hacked or not, right? Has it been compromised or not? So, should you treat this as classification or regression? Which problem belongs to what? Please answer, please.
The second one should be treated as classification.
First one is regression.
Second is discrete.
That's correct. Awesome.
2 and 4 both are right. Like you can use logistic regression, that can be.
Yeah, logistic regression is for basically classifying. Yeah, the right answer is 4. Seems most of you are following. Then we are done with, we have seen regression and classification so far. We'll look at clustering, and again my colleague Anshuman will take you guys through. We have just designed those static around so that you won't be bored with one person's voice.
Yeah, so Satya explained to you what is regression and classification. They are form of supervised learning. Again, I will just go through again what is supervised learning just in one line. You are not given the labels or the classes, the Y's here. You just have the X data. First thing is you have to find the Y, and then you also develop a model to basically classify, put a unseen instance into those Y's, which Y belongs to. Example can be you have a lot of news feed like news articles. You process them and find the categories which you can fit them into. Like common categories are sports, technology, politics, and all. But there might be some trending topics like currently under sports there is Ashes series going on, so that can become one topic. So that is also timing, finding the categories also. So an algorithm will find the categories and put the news articles under them. Any news article it can also classify. That's basically clustering. So this is like kind of a 2D example that there are some points X and Y. Basically you can say X1 and X2 are there. So the equation is Y is equal to Fx. Y you have to find X is what is given. So first thing is you discover all possible Y, discover all the clusters or the groups you can make out of them. So you discover that, and second thing is you learn how to put a new instance into in this group. So you say I get a new instance, which group it belongs to. So that model I also have to develop. Say a new news article come, where does it fit into? It is sports or technology or politics or. So this is a form of unsupervised learning. We haven't given them the Y's, classes, labels. The algorithm itself has to find those also and the model also. So just again one more question to just test your understanding around supervised and unsupervised learning. So probably go through.
Third option, B and C.
Yeah, good. Absolutely. So, as I said before during the start of the presentation also, we are not going too much detail detail into the technical details, like teach you how to work out your algorithms. But I'll just give you a list of algorithms because these are all in their own right. They are very big topics themselves and need a full lecture. So can't cover all of them here. But these are some of the common types. So regression is linear regression where we fit it into a straight line or a curve. That just Satyendra showed you. One more advanced type is ordinal regression. Under classification, we have support vector machines. That's a kernel-based method. We have methods which fall into trees structure: decision tree, decision forest, boost tree, decision tree, random forest. Then we have artificial neural networks that we basically simulates how our brain works. So they're based on that actually. And that's why the term neural. Logistic regression. This is regression also and classification also. So it falls under classification. Bayes learning, that's probability based classifier. Under clustering, there are many algorithms like K-means. You might have heard this term, very common. There are hierarchical clustering, DB scan, all kind of algorithms. So you can actually be interested. You can go through some of the basic ones. PowerPoint is failing us.
The machine started learning.
Probably Microsoft employed
Or
some.
rather, it didn't start learning.
So Microsoft, that's why they're not doing much machine learning. That's the problem. So briefly go through the what can be the possible common applications of regression. So like companies, e-commerce companies you see, right, they offer a lot of promotion discounts. How they find the right price, like how they find on this particular item I will offer 40%, it will be the most beneficial for me. So they try to predict how the price will impact the demand or the sale, basically the demand curve in economics. So they try, that is one thing that regression can predict for you, and based on that you can maximize your profit. So whenever some promotion is offered, they actually do this in their background. Advertising effectiveness. So if some promotion is run, how effective it was, how can you actually relate it to the sales. So we before the promotion also we have sales data, then we run the promotion, we have our advertising spend and the kind of advertising we do. Can be TV advertising or can be on the radio or various mediums, internet advertising. So we try to find out which effect, how much effect one had on the sales. So that can also be done by regression. Risk analysis, like you buy insurance, like health insurance, how do they price that? They look at your data, age data, your medical history, your family history, your work lifestyle, things like that, and they try to fit it in a model like how much health hazard you have in next 1 year, probably what will be your probable spend, and that's how they price the health insurance. Day-to-day examples can be car valuation. You use like carwale.com and sites like that to you put your second-hand car data, they give you a price. Weather prediction, everybody must have used how weather is predicted. We have decades and centuries of weather data. We predict if today the conditions are like this and this month is now is August, so probably tomorrow what might be the prediction for the weather. So just to show the visuals, like this is how car valuation happens. You give the make, model, variants and the fuel type and how old it is, things like that. It gives you a valuation because they have a lot of data that this kind of car, what it sells for. So from the experience they learn and give you a prediction. Same for the weather. We note all the weather data, we collect that, so we can predict the forecast the weather. For classifications, classification techniques, what can be the probable applications? Spam filtering or email classification, you all must have used Gmail. This new feature added a few months back that they put tabs onto your email, primary, promotion, social updates, things like that. So they classify emails automatically into them. So that's a kind of classification problem. MRI classification, ECG classification in the health sector, like you make MRI done for some tumor or ECG for your heart. So all that data you usually not popular in India, but yeah, outside they put it into their own system and give you a prognosis. What can be the probable cause, and then they go from there. Web advertising, so like Google and all, but they when you browse any site, they look at your cookies and from other things, browsing habits. They try to predict, given a particular ad, what will be the probability that you will click it. They will show you the ad with the maximum probability. That's also kind of classification to show the ad or not. Those are two classes. Day-to-day examples can be even these are complex examples. Facebook, face recognition. Facebook, when you see a picture, it asks you to tag someone, give you a suggestion to tag. Is this person? It automatically recognizes face. NLP, Siri, and the Google Voice service you might have used. You can give voice command to your phone. Biometric, it's in the campus also. Fingerprint scanning. So this is how basically face recognition works. What they do is usually they have some points on the face that they try to find in the picture, and based on that map, basically the distance between them, those points, and probably the angle between the lines, they try to map a face. So even if it's side angle, they are able to recognize the face. Voice NLP is a lot of things, some voice recognition, text to speech, speech to text, then language translations. So all that you must have seen, the applications. A lot of Google tools available on it. So these are all classifications. These are like more sophisticated versions of classification. They are mostly classification. I'll just show you one video next for the text classification, how it happens. Like you have a handwriting, and actually the algorithm can recognize what you are writing. So it's an old video, early 90s. It's an old field, as I said. Even that time the computers were not like what we see today. But they were able to run those algorithms and do the digit recognition. There's no voice in the video, so I'll provide that. So what they are doing is they are putting the paper under the scanner, and that appears as a handwritten digits. So the computer is recognizing it real time. They are trying to various font is a printed digits also.
It's not failing at all. Algorithm is not failing at all.
So this is kind of a messed up handwriting, but still it's able to recognize that. Various fonts, fancy fonts, they will try. This was like early 90s, so with that computation power, they are able to do that then. So you can imagine in 2015 what is possible with all this. So I'll hand over to Satya for some of the closing slides.
Guys, we have got a couple of slides, that's all, to finish the presentation. We might overshoot by 5-10 minutes, but we should also appreciate that we have started a little late because people kept coming in, and then there were some technical problems as well. Just 10 more minutes there with us. It will be useful. Let's look at some of the applications of clustering. Like we said before, the clustering is used to find structure and commonalities in data. We don't give any labeled instances to the data. One of the applications is, I'm sure anybody who has worked in banking sector or who has a little bit of banking domain knowledge knows this
Customer
customer
relationship
segmentation.
model.
Basically, what you do is you feed all the data about the customer demographics and transaction details to the algorithms, and let it find hidden patterns and clusterize basically the customers into different tiers. For example, one of the banks, they have come up with tier 1, tier 2, tier 3, and based on tier, they will provide advisory services, dedicated advisor or advisory group, or they do not have advisory services, they just need to call up for customer care based on this classification. And then the second one is color quantization in computer graphics, which means typically when you click a photograph in mobile or any normal camera, before it stores the image to the disk, it does a little bit of processing to reduce the size of it. Basically, every pixel has got red, green, and blue in different intensities. So it will try to find a kind of pattern. It will try finding pixels which are closer to each other and kind of normalize the color in order to reduce the size of the image. That's how DSLRs will have a raw mode where you can shoot and save the image as it is without this processing basically. Okay. And then this clustering is also used in bioinformatics. Basically, you have a lot of pathogens. You can subtype them based on the DNA data. There is something called DNA sequencing and DNA arraying. There are a couple of techniques which medical field people will employ, and they subtype the pathogens. The use case of that is when you have different categories for the pathogens, right? You can try developing the drugs which will work for that set of pathogens. Basically, you can more focus on each group, right? So, apart from this industrial use cases, you can find some day-to-day use cases as well, like grouping of related articles, which you actually see on a daily basis, right? And then social network association analysis. We'll see a couple of slides on this. This is Google News. As you can see here, there are two links over here. The first one, I'm not sure if it is very visible, but the first one is from NDTV Sports. That's the source of it. And the second one is for IBM Live. A couple of months ago, Sachin was voted as a best test player. So Google's algorithms behind the scene were able to clusterize basically the stories and group them together because it's about the same person, same story basically. Right? This is from Google News. And then this is social network analysis. On the left side, you can see Facebook. For example, Facebook will look at your interaction data, basically whom you are texting more, on whose post you are commenting more, whose post you are liking more. Based on those preferences, your news they will basically divide into coherent groups. They will divide the user base into coherent groups, and your news feed will take inputs from these groups basically. So if the more you interact, they might show that they might actually rank the post higher in your news feed. So those are the applications for iteration, classification, and clustering. Now we look at other applications which are we have picked up a couple of interesting and fascinating applications so that it will interest you. You will know what all kinds of domains machine learning is being employed in. The first one is autonomous self-driving cars. Like I was saying before, it is employing reinforcement learning. You will see, there's only one slide before the presentation finishes. After this slide, that's a video for 3 minutes. It will show basically how the self-driving car works, how it color codes the objects around it. For example, pedestrians into yellow color and bicyclists into red color, trucks into green color. How it will classify and how it will find the safest path for itself. You will see all that in the next video. And the second one is hand digit recognition. It employs basically artificial neural networks for classification also, like Anshuman was saying. And we talked about that, we talked about this, and the third one is YouTube video and Flipkart product recommendations. I'm pretty sure everybody in this classroom would have seen this. Basically, the algorithm which is being employed is recommender systems, right? It will try finding behavior of consumers and it will give product recommendations. You would have seen customer like you who has bought this has also bought this. So these are basically being done by this kind of system, right? And then people from programming background knows what Stack Overflow is. That's a portal wherein you ask questions and you get answers by the people who has got knowledge on it, right? So Stack Overflow is employing a model which predicts basically which new question will be answered sooner and be closed sooner, kind of based on the past data it has got, right? That's what the use case is. So you see what kind of domains are involved, what kind of domains are employing. It's like huge area basically. And then this is one of the other fascinating facts I have picked up from, there is a company called Marine Explore. It is working in collaboration with Cornell University. They have devised a model which basically takes the recordings of the sea, ocean, and then it will try finding the presence of shark, right? They have built a model. I was just reading through some of the blogs, and then they have built a model. It was having 72% accuracy. And then what I've done is, are you guys aware of Top Coder? It's a website basically for coding contests. Similarly, there is a website called Kaggle, Kaggle, that is for machine learning basically. They have put up a challenge on this to improve their percentage from 70 to beyond. And then within 2 months, they have got a lot of people who have participated in it, and it was improved to 98%. So basically, when ships are traveling in the ocean, right, they can predict up to with accuracy of 98% where sharks are lying, so that this shipping accidents with sharks, collisions can be avoided. You can see basically it's a real life contribution actually. You can even see that working in action. And then there is a company called Seal. They have filed a patent in 2012 for something they have done, and the patent was approved in 2013. That is to look at the accelerometer data. These days, all smartphones has got accelerometer in it, and the way a person moves and holds the phone, mobile phone, smartphone, based on that, they are trying to identify a person to see whether he is the authorized user of the device or not. They have got a patent for this, for unobtrusive way of identifying a customer. And then this is very typical one, anti-software packages. Basically, when you talk to internet, you send a couple of packets and you receive a couple of packets. So bunch of packets basically. So antivirus software employs machine learning behind and try inspecting the packets based on the data it has already got, based on the fact it has got. So it basically tries to improve the protection level. Okay. The last one is almost similar to the shark thing. Oregon University is actually trying to build a model wherein they try to find out the bird species based on the recordings around the paddy fields and something like that. So that's one of the. And then we are almost there.
Video is not starting.
One second. That's what is the last time we are
This was.
We have tried our best to start on time and finish on time, but sometimes plans don't work. That's life. Once again, this video doesn't have voice because of technical problem. I will provide voice for it. I'll try and see because she explains quite well as compared to me. So I'll see if we can put it. Just watch and see how the algorithms behind are classifying the objects. Just watch and see how the algorithm behind are color coding the objects and trying to find a safe path.
Here, finding a safe path is very easy.
For a vehicle to drive itself, it needs to know where it is in the world, and it also needs to know what's around it. Based on these factors, it needs to be able to make smart and safe driving decisions in the real world. And once you get in the car, you start to get a real feel for the way the technology works and what it's like in real driving situations. So there are a few things that have to happen before the car can safely drive itself. First, it has to figure out its location in the world. So we use GPS, but GPS isn't always that accurate, which is why we rely on our other sensors like the laser, which picks up on details in the environment that help us identify a more precise location. So think of the sensors like the car's eyes and ears, but with eyes that can see far off into the distance and 360 degrees around the car. And the great thing about having all these sensors is that they can talk to each other and get cross-checked information about the environment. So while we take in a ton of information using our sensors, it's our software that really processes all this and differentiates between objects. All these objects are visible on the laptop that the safety drivers use while testing the vehicles. Based on what the vehicle senses and processes, these objects will be represented by different colored boxes. Cyclists will be red, pedestrians yellow, and the vehicles will appear as either green or pink. These boxes demonstrate the processing that takes place within the software. And think about the complexity here. People look different, cars have different shapes and sizes, yet despite these nuances, the software needs to classify these objects appropriately based on factors like their shape, movement pattern, or location. For example, if there's a cyclist in the bike lane, the vehicle understands that this is a cyclist, not another object like a car or a pedestrian. So the cyclist appears as a red box on the safety driver's laptop, and the software can also detect the cyclist's hand signal and yield to them appropriately. When our engineers think about where the car should drive and how, safety is always the top priority. So the vehicle takes into account many things like how close it is to other objects or matching speed with traffic or anticipating other cars cutting in. For example, as a passenger, it can feel a little uncomfortable passing by a large vehicle on the road. Our engineers have taught the software to detect the large vehicles, and the laptop shows them as larger boxes on the screen. As a vehicle passes by a large truck, it will actually keep to the farther side of the lane and give ourselves a little bit more space. We've also taught the vehicle to recognize and navigate through construction zones. The vehicle sensors can spot the orange signs and codes early to alert the car of any lane blockage ahead, and then we can change lanes safely. Another thing that's really important is for the vehicle to drive in a naturalistic way, because when it's natural and the car abides by social norms on the road, it's also safer. For example, at four-way stops, people typically rely on eye contact to communicate whose turn it is, and in our case, the vehicle inches forward into the intersection to indicate its intent. So my role as a safety driver is first and foremost to keep the car, myself, and everyone around me safe. And in addition to keeping the car safe, I also provide detailed feedback to developers and let them know the car does anything that maybe I wouldn't have done personally. Maybe the car wasn't assertive enough in a lane change or wasn't fast enough at a green light. We provide the detailed feedback so they can fine-tune the whole driving experience. By getting out there and driving in the real world, we're getting a better understanding of what exactly it's going to take to improve the safety, comfort, and ease of transportation. And that's really what our project's all about.
Guys, I have taken this video so that you will know how it is actually processing and how it is color coding the objects around it. But this is a little older video, and now Google has made even more progress in this. They have got a car and they have eliminated steering wheel, accelerator, and the brake completely. It is just a car with none of them. There is no manual intervention at all. So that's the progress they have made as of today. And in case you guys are inspired from our talk on this introduction to machine learning, we have put up some resources.
You can actually, this Coursera site is a very good resource if you want to watch video lectures. Professor NG from Stanford University is a good thing to start with if you want. Some of the books, Introduction to Data Mining by Dan Kumar Steinbeck, Pattern Recognition by Bishop. Other than that, if you want to learn something technology specific, then probably can start with learning R. That's a widely used tool in machine learning.